Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's a fix. Yeah. Is it okay?
Yeah.
Okay. Yeah. Thanks.
So it's my pleasure to introduce to you Professor Lin Guan. He's currently a professor at Ryerson University, and probably better idea to close the door. He got his bachelor's degree back in 1982.
True. Yeah.
From Tianjin University. His master's degree from Waterloo in '85. And his PhD from UBC, which is not too far away from here, back in '89. And he was an effective member at University of Sydney from '92 to '94, right?
'92 to 2001.
2001, and yes. He's now a Canada Research Chair. That means he brings a lot of funding to his projects. And today he's going to talk about two projects. One is Bimodal human emotion recognition, and the other one is peer-to-peer streaming. With that, that's Professor Lin Guan.
Okay. Thanks, Yung. Actually, Yung gave me when I tell him, what do you want me to talk, I gave him three topics. He said, I will choose two of them. That makes my presentation pretty hard because they are not related. It's pretty hard to put them under one name. So I decided to add a little bit. That's the introduction of what we are doing there, so that then I can just use that as a kind of example of what we are doing, so that makes the presentation more coherent. So to start with, this lab was established in 2001 when I came from Australia, Sydney, Australia. Essentially, I brought lab in Sydney to Ryerson University in Toronto. And of course, we do basic research, applied and applications and applied research, but the focus is on applied research, media indexing retrieval, human-computer interaction, streaming media over collaborative networks, and some bioinformatics. And here are just some sample applications which could be. It's interesting why it doesn't work. Okay. Yeah, which we already started the application, but others we are actually looking for partners to apply the technology. I think I should acknowledge the research support from the Canada Research Chair Program and other federal, provincial, and university fund. So most of the research, you can see that most of them are actually, the kind of federal fund and the provincial fund, which are not industry related. And now I just want to, this is what we are doing at the IML. And the three layers here, the basic research, it's essentially everybody's doing some aspect of that. And I just will use a few slides to touch the applied research part. Why is this? Indexing retrieval, human-computer interaction, and coding and transmission. Okay, so in media indexing retrieval, we actually focus on, right now we focus on, the kind of interface between content-based and concept-based, because it is acknowledged that content-based alone will not do the trick. So we study, the kind of, what kind of, how do we fill the semantic gaps, and how do we propose a new model in indexing and retrieval. So what we come up with, are two things. One thing is a completely concept-based model, which is we call that it's based on what we call generative grammar of elemental concept. And the next one is more conventional. It's mostly content-based retrieval, but here we use some nonlinear models in matching, and to somehow mimic a human mimic a human perception. And also we use self-organized learning to reduce the relevance feedback, so that we use some relevance feedback, but mostly we try to optimize that process so that this kind of human interaction can be somehow reduced, to minimize subjective error, which could be introduced by excessive human participation. And the second part is human-computer interaction. We do two parts of work. The first part is the bimodal human emotion recognition. This part, I'm going to come to this part later. And then the human-computer interaction, which is modeling and recognizing human actions. So essentially, based on some of the basic human models, we come up with an idea what we call a dynym, which is in analogy to phonemes in speech recognition. To use that, we come up with this kind of hierarchical model. Dynyms will, a skill is a series of dynyms, and then activity is a series of skills. Which this is almost completely in parallel with speech processing. If you just consider a two-dimensional motion here, but for three-dimensional, of course, it's more complicated. And so, and then the last part is the coding and transmission part. What we do is that we essentially we start with the centralized peer-to-peer model, and then we extended the work recently to the kind of more general collaborative network. Essentially, it has a strong component. It's two complementary components. I'll come to that part. For example, you have 3G and wireless LAN, that kind of combination to transmit the scalable video. And so also we started as a kind of multi-pass streaming video, etc. And of course, hopefully that this will become a reality. And then this is the bioinformatics. This is, I haven't updated the diagram yet, so this part is not there. But here is it's enhancing, visualizing microbiological data. I don't do DNA because I have some kind of objection of working on DNA, but I wouldn't mind working on this part. This is these are the chromosomes of some plants. Okay, how do that's how the kind of a microbiologist can get from the confocal microscopy. You can see that there's a lot of feature. It's not very clear. So what you can do is that you use some image processing, 3D image processing and visualization techniques to get to the microstructure of the chromosomes. And
so who do you partner with to make use of the result?
Okay, for this one, actually, this part is my work at University. We work with, there is a very strong group in microscopy images. But here, we actually, in our university, there is a professor who is doing bacteria. Okay, the structure of bacteria in, for example, wastewater. Okay, that will help them to start a new method to treat the wastewater. Now I'm working with him, but this is a much harder problem. We haven't got anything out yet, but the baseline technology is there. Okay. Okay, so now this is just a very brief introduction about what we are doing. And then I think I will jump into the first technical presentation of first technical part, which is bimodal human emotion recognition. And this one is mostly based on to identify features, feature extraction and selection, and recognition architecture. Okay. Okay. This is done by my student Yongjing Wang. So we'll have a short introduction. This is essentially based on his recent presentation, and this slide will be used for also used for ARCASP paper accepted in Philadelphia. The audio-video feature extraction, recognition systems, and some conclusion here. And first, in introduction, the general background. Okay, I got to admit I'm not an expert on this part, but what I know is that the different kind of your brain I actually handle some kind of audio, some kind of video, visual, and some actually coordinate the kind of the fusion of the data to get a multimodal representation of human emotion. So the applications, I don't think I need to make this one very too much, but you can see that, for example, consumer relationship call center. These are the probably the typical example. You can use human emotion to help to treat the customer very nicely, so that they feel comfortable about the customer relationship. Because based on what customer said and the visual expression, you can somehow adjust what kind of reply you should provide to make customer happy, because the customer is always correct, right? We know that. And then here, what we want to do is we want to investigate. It's an initial investigation to a language and cultural background independent system for the recognition of human emotion. For example, what the data set is not very big, but we have tried our best to separate the training from testing. I will explain later at the experimental part. So essentially, we have 8 subjects: 2 Italian, 2 Chinese, Mandarin, but they have different kind of accent. 2 Pakistani, 1 Persian, and 1 Canadian. 6 languages and 6 emotions. This is a kind of debatable point, because some people think that there should be more emotion. We have a theater school there, and some of the performer taught us that there are 150 emotions, but apparently you can't use that kind of large class, which will make the analysis very difficult. So you can see the top one. This guy is an Italian who is showing his showing. Oh, you have to use this. Showing. Disgusting, disgust. Okay, and the bottom one is speaking English to show happiness.
I got A+ in that course.
Okay, this is some example. We actually found that for different kind of different people speaking different language with different background, the expression could be quite different in terms of the feature.
So most other people's research now, the state of emotional research, do they focus only on the culture?
Most of them. Some of them even, well, this is all male. Okay, I found a lot of them are all male or female. For example, there is a Japanese database which is all female. And this research is actually still in a very early stage, because, to be honest, I haven't seen any serious journal publication yet, to be honest. Okay, yes?
Are the subjects trying to act the emotions, or are they in some situation?
Well, that's another thing. Okay, that's another thing which haven't been decided on how to should structure a database, because this is, yes, we ask the subject to show the emotion. Okay, and there are another approach is to hire professional actors and actresses. Okay, and the third one, I think that should be the best. You have hidden camera. You get people in, he or she doesn't know. Okay, and then you try to make him happy, or but it's pretty hard to make people to be angry. You don't want to do that. Okay, but maybe let's just like candid camera, tell him afterward, right? That should be the best setup, but we haven't done that part yet. Okay, to use actor and actress is actually not that good, because for human recognition of actor and actress, they can only get 70% or 80% correct. I found that's alarmingly interesting. It's very interesting, but it's not very good. Okay, so these are all students in my lab, and this is the overview of the system. We have audio features here, which essentially we have a prosodic, MFCC, and Formant features here. And here is the video part. I got to say, the video part we just use. For this part, we did some more decent investigation, but for this part, we took for granted from the published literatures. Just use Gabor wavelet to detect face and do a Gabor wavelet, transformation there. And here, this is the part we do the. Here is the feature selection, and then here. We actually studied several architecture, but this is the final architecture we decided on, which is actually in the spirit of weak processors. We know that sometimes the weak processor, the combination of weak processor can do something the strong processor, a single strong processor can't do. The typical example is the face detection by what is that? I forgot. Yeah. The guy who is actually in Microsoft. I don't know if he's watching this presentation, but if he is, okay, hi. And for face recognition, use what is that? The technique? Yeah, AdaBoost. Yeah, it's several, tens of hundreds of different weak processors. Here is the spirit is essentially the same. Okay, I'll come to this part later. Okay. And here is the feature audio feature representation. Okay, first we do the prosodic. Prosodic here, we do the noise reduction, do the leading and the trailing edge eliminations. Here's but the one thing, I think we should have started, the voice and unvoiced, but we didn't do that.
By prosodic, you mean just the pitch?
Yes, that kind of things, Okay. Sorry, that's the feature. Okay, here's a. Okay, now. If we go back to this slide, I think this is essentially, not too much. This just show the windows. We all know this. Okay, it's nothing fancy here. And here you can see that this is from 6 different languages. You can see for some of them, from here, I can do some. Well, last night I did some prediction, because I can never remember which class what works well for the audio. I did some prediction when I do the final preparation. I said this one will work. This one, anger and surprise should work well, audio, because the similarity is here. And when we come to the final, experiment, you'll find that this is true. For the others, you can see that there are some kind of variations. Also, for some of them, for this, I think they are somehow, but this one is quite different. This file you can see the somehow similar, but this one is quite different.
So I don't understand. Since the data are coming from different words, you cannot constrain the user to say whatever.
We give them. Yes, we use different sentences. Okay, each.
If that were the case, then why do you ever use MFCC? MFCC has most of the information about what the words are.
But the thing that
that's kind of now it becomes a novelty.
But the thing that MFCC is not very good for the emotion part. It's good in speech recognition. But it's, as I will show you, actually, essentially this one alone can give you a very good result. Plus MFCC and Formant, which will
only if all different speakers say the same thing.
No, they don't say exactly the same thing.
If they don't say the same thing, then if one says A, the other says B,
then
the difference between these two will outweigh whatever emotional difference you have.
Well,
E1 is R. You do the special one in MFCC.
Yes.
The difference will be huge.
I think so. Yeah.
Unless everybody say the same thing.
No, it's impossible because 6 languages. How can you expect them? Even they say the exactly same sentence in different languages, it would be somehow different. Yeah.
So in that case, you probably need to use a very high order MFCC.
Well, you are probably right because this is okay. You are probably right. Okay, this is a very, very good point. Okay, I will tell my student to try that because right now the proof is that the prosodic features are the best right now. Okay, this is the kind of typical prosodic feature used in emotion recognition. 25, and here you have said MCC. Probably probably the order we use is too low. Okay, we probably should talk about this again to see how this could be improved. And then the form frequency features here. This essentially we just did the feature. You can see that it's actually quite simple. Just calculate the mean, median, standard deviation, etc. And here is for the visual feature extraction. As I said, it's actually the approach for this part is actually quite simple. We didn't do too much in this area. Although actually my home field is image processing, but this is a kind of just another round. We did some very simple operations to make the face clean, and then do the Gabor, Gabor wavelet, and to extract the Gabor wavelet features. And so you can see that different directions, 4 scales, and 6 orientations here, And this is an example for one of the, the kind of the Gabor filter. This is the Gabor filter bank, which shows different direction and different, scale here. And here is an example of this face. You got this filtered direction, different direction, and different scale. Vertically, that's horizontally, it's a different direction here. And then, okay, we from here we actually have 48 visual features from the 24 filters. Okay, it's just mean and standard deviation here. And here, the experiment performed on 500 video samples from 8 subjects speaking 6 languages, as I said. Essentially, what we did is that we try to maximize within this sample, limited sample. We try to maximize the kind of the difference between the training and the testing data. Essentially, we use six of the subjects in training and 2 subjects in testing. There is no overlap at all here. We use the 2 feature selection method. One is principal component analysis and the stepwise method to compare for feature selection to see which one is better. And we tried several models to see which one is gives you best classification. This here is actually something quite interesting because the conclusion is that the Fisher linear discriminator analysis is the best, which, well, intuitively shouldn't be the case, but it shows it is the best. Okay, I think I will have some kind of explanation to see why the other model doesn't work as well as FLDA. Yes.
So when your training set and your observation set, do you have the same person with the same expression on both sets?
No. Let's say one person, all his expression will be either in training or testing. There will be no overlap. So 6 people, we use 6 people in training, 2 people in testing.
Okay, so you separated.
Yeah. Yes. Yeah, I think that's the maximum possible separability you probably can have here. Okay.
So how do you make use of the sequential information there? You
What?
get the video, huh?
Yes.
So you got the sample.
Yeah.
And then you treat different samples of the video as
Okay. The video part actually we did again. It's very simple. We actually didn't use the motion part. We just select the keyframes, a couple of keyframes. Okay, to do that. I know that we should use the part which is in progress, but this is just what we got so far. Okay. So here that are the same models we use here. GMM, neural network, came in, and FLDA. Here, this one is a linear one. This is pretty simple. This one, this one is your typical nonlinear, and this one is, more than a linear model, of course. Okay. This is the result. It's the first result. It looks quite interesting. You can see that. Sorry. This one gives you the best result. I think my explanation is that, you got too few samples. You don't have enough samples, so the nonlinear filter will not work very well. Okay, that's the only explanation I can offer here. Because from feature selection, you are going to see that the stepwise one, which is not a linear one, works better than principal components analysis, which actually shows the problem should be at least piecewise linear or superlinear, whatever you call it. Okay, so but here you can see that the result, none of them is very good, even though you could reach 70. 70 is not that.
So why the visual information so weak here? Almost giving up away.
Yes. Well, because what I can say is that the visual feature we choose is not very optimal. You don't have any particular shape feature there. It's a transformation of the whole face. Yeah, that's right. Yeah. Okay. What is this? Actually show each of them. The class. As I said, you see, anger for audio, anger, and surprise gives you the best result. That's what I predicted there. Okay, because you can see the kind of uniformity in a spectrum. Okay. And then, well, we thought we should do some feature selection because we all know that sometimes you use all features, which is not very good, especially if there is a kind of dependency correlation among the features. So it's better to take out of this problem. So for PCA and a stepwise method, we selected 40 and 45 features respectively. This is the reason for that. For PCA 40, we use that kind of 90%, representing 90% information, use that point as a cut. And for stepwise, we use the point which gives the maximum discriminating power, which is 45. Okay, so you see the origin of 153, and we reduce that to just 30 to 40%, and PCA actually give you a worse result than that, and stepwise give you better. So which actually shows that the problem shouldn't be a linear problem. It's more likely not linear, but because of the too many features there, so that the nonlinear algorithm, classifier actually works worse than the linear one. So then this is again for different kind of result here, and but then we thought that this is not good enough. Let's try something else. Essentially, what we did. This is we use modular structure. This is the main part. It comes here from feature selection, and then we do the modular structure. For each classifier, it's one to many. Okay, 1 to 5. Okay, just one class, just specialized for that particular class. This is nothing new, but the point is that we actually select feature for each of them. We don't use general feature selection. We select features for each of the classifier. So the conclusion is that each of the classifier actually will have different kind of optimal features here. Okay, and then I come to here. We have some other rules to further improve them. It's essentially, it's again a quite number of weak classifiers. For example, you see here, if n, that is a number of class greater or equal than 2 or equal to 0. So what I mean here is that n is the number of output that exceed 50% over 0.5. So you can't make a decision, and then in that case, you have fit this into a global classifier to do further classification. And this one is actually quite complicated. It's actually you have a 5 classifier decision, 4 classifier decision combination, 3, 2, 1. So it's a very complicated process. And altogether.
So if different classes have different features, then how do you compare the score? You cannot compare the score, right? You cannot compare everyone.
Well, I know what you mean here. Okay, but
typically it's a very subtle problem.
yeah, but
you do that, but you need to have different kind of decision.
Yes. Okay. Well, essentially, what we just our consideration is just we just want to have optimally separate this one from the other, because I know, and then we'll do the fusion part. Okay, when we do the fusion part, how do you compare them? I know that is your question.
So suppose you build a Gaussian classifier.
Yeah.
Then this feature may give you very high score.
Yeah.
The other feature may give lower score.
Yes.
But
Yes.
this is more likely than the other.
Yes. You're absolutely right. Okay.
So the base feature that is common across all the loads.
There are some features which are actually even for this separate feature selection. There are some features which are universal, but others are different. But I think your point again, you have the point, and I think that's very interesting. To first have a baseline, feature set, and then you study the particular characteristics. That's another way to do that. I think this is a very good point. But anyway, by doing this, you can see that for the second one, the accuracy is going to 82%. That's compared with the original 70. This is the quite significant improvement here already. And you see here, this is just showing the experimental result. Okay. So, and here we also did cross-validation here. In cross-validation, of course, it's take one out. To use take one out, we just want to see, to use this, how good it could be, because here you have more samples in training. Testing is more samples in training. Okay, the result is almost 90%. This is, I think, it's pretty good. So which actually gives us an indication. If you have a large sample of data, you probably the performance should be improved. I mean, that even in this kind of scenario, the performance should improve That it looks like the kind of the discriminating capability is there for this kind of approach. Okay, let's see. Okay, and this is the. Oh, I think I should show you about the prosthetic feature, because I think I promised to tell you that the prosthetic feature actually dominate. No, it's already go. There should be one which show that. Yeah, you see here. Prosthetic feature alone, 65.7%. You have old audio feature is only 1% more, less than 1% more. So, yeah, this actually confirmed everybody. Yeah, okay. But I think your suggestion to use the higher level MCC.
The higher and higher orders of
yeah.
MCC, you essentially get more and more prosthetic.
Okay.
So there could be some overlap.
Okay. Well, but then.
If they're all lower, maybe you get better.
But then you use feature extraction. You can throw out. Yeah. Okay. Yeah. Good. Yes.
So 90% accuracy, that's actually very high.
But that's a cross validation. Think about that. That's not the real thing.
Yeah, but even with the previous one, 78%.
82 actually.
82, that's pretty high.
So there's no standard database to test this kind of information at all?
This is no. Well, this is. Well, I know Tom. I was actually inspired by Tom, but you know what? Tom this time he was in PCM. He still used 98 example. I was surprised actually.
So my question is actually, even at 82, that seems to be pretty high. Have you tried to ask humans to watch the video and then ask humans to see how accurate? My suspicion is humans may or may not reach 82.
Well, you are right. For actor, as I just mentioned, for actor, human can only recognize between 70 and 80%. And actor should, we think actors should do better than normal human beings. But sometimes.
Yeah, but if you just look at the video, you probably cut off the context. If
That's
you know
possible.
what content it is,
Yeah.
you don't even have to watch those, so you know
Yeah.
what it's saying.
Normally, computer shouldn't work as good as human. But I have a very interesting content example, which many years ago when I did what do they call it? Salt and pepper, to try to clear the salt and pepper. Salt and pepper noise. Okay. We actually create an image which you can't see anything, absolutely nothing. But use the algorithm, it actually recovered the pattern. That did happen. Yes.
Do you feel, maybe you tested this at some point, how good your algorithms could have done if you just trained on a certain person and then tested on that same person?
That's what.
Second.
That's what we did. That's what we did.
I mean, just that person. Train just on a single person, and then
Or that,
subsequent.
well, there are different kind of scenarios. Do you want him to use the same kind of sentence structure or use different sentence?
I mean, not requiring anything else.
I think
Just
for
personalized training.
I think this is actually very fundamental kind of aspect. I actually, when we do the presentation at our university a few days ago, the student did this. Actually, he got a similar question. This is probably something we should do. But I think, I think it should be higher. Definitely should be higher. Because you throw out all this kind of language and culture background. It's just the same person speak the same language, use the same impression. Even he use different kind of sentence or phrases. It's still it's him, right?
And it wasn't clear to me. My simple question on the audio: if you were looking really at the difference between like a baseline of that guy talking and the emotion, or are you just looking at the absolute of the emotion, trying to correlate that?
Well, at this moment, we didn't study the very baseline part, but I think again you at some point we should go back for that. This is I think I got a lot of topics for the student. That's great. Yeah, that would be very interesting actually. Yeah.
I have a question about the video processing.
Yes.
How are the images aligned where you take the
Well,
features? Are you taking them at specific points on the face?
Well, I think, we choose that kind of, key frame in most of the time, it's just we don't use one frame. We use a number of frames, 2 or 3 frames equally, just sample within that sequence, and use that kind of, you.
So are you hand labeling the location at which you're
Well,
filters, or
the length. Okay, right now it's very simple, but we have actually a quite interesting approach, which probably can do a better job. But that's we use that for image retrieval, video retrieval, which is actually it can based on the kind of probability of occurrence of a particular section, in the video. But right now, it's very simple. It's just we know the length of the video. We just tell, okay, for example, just 5 frames from each segment, and then use some kind of weighting scheme to get the.
No, but I'm asking about how do you process each frame? So take one of the frames.
I see. What
points do you look at in the frame? Do you look at all of the pixels?
No. Of course, first we detect the face. That's the first thing. Okay. Yeah.
But are you applying the Gabor filters at specific points, like?
No. This is just to the face. Just to the face. As I said, we just for the video part, we can actually do what we did is actually very primitive. It's just we didn't do too much, we get here too much.
I just wanted to see if that was the reason that the performance on video is
Yes.
so poor, because usually performance on video is better than audio.
Not necessarily true. Not necessarily true, because it's just from the very beginning, Tom's work and some other guys' work, it shows that for some it's expression dependent, emotion dependent. For some emotion, it did very poor, but we just hope that they are complementary. Sometimes they are complementary, sometimes they are not. But the joint effort could still make things better. I think I should have one example.
It's hard to compare across different data sets, but I've seen
Yeah.
results on video that were
Yeah.
pretty good.
Yeah. Okay.
rivaling
Yeah.
your audio, your
Yeah.
audiovisual results.
Yeah, but I think one reason I think Lee already mentioned that ask me, it's exactly what you ask, is because of the visual processing. It's very simple what we did. It's really simple. Okay, just cut the face and.
So in Tom lab, so what kind of fancy technique that was using for the video processing?
Oh, okay. I still remember Tom's talk. He used actually the grid model. Grid model to model this kind of salient point. Okay, to get the kind of. Yes, he has that, but but it's very interesting. He didn't show anything new, because I know the Rico is still doing that. He's in University of Amsterdam, right? He's still doing that part, and actually he had a talk at PCM, right? On this kind of, but Tom didn't use that part. Tom still used 98 the result. Okay, the 2-person scenario. Okay, yeah.
Also, you have 6 expressions here, but in general, I think some other stuff that I heard a lot more than that.
Well,
so is that because those 6 emotions have been identified to be the most important ones?
Well,
whatever application you're looking at?
Put it this way: from the papers, if you count the histogram, this one got the highest. Okay. Some people they add neutral. I think neutral. I think we should add neutral, because that's where I think neutral should be there, because this is the most common expression. And for some people they use 5, 4. For some people they just use 1, 2 expression. So this area is it's quite established in my viewpoint. Okay. All right.
John actually has a very good point. If you don't allow, say you face detect, right? But you cannot trust the face detector 100%.
You're right.
Sometimes you need allow.
Yeah.
Then you extract features where
They don't correspond to the same point on the face, and then it's harder.
You're absolutely right. But in this study we did very simple. Just against the uniform background, so there's no problem about.
So why don't people establish a common database in this field? If it's in one field, right, somebody has to sort of maybe a list or something.
Well, maybe you can do that, Lee. Yeah.
Sometimes the easiest sell is something that's secret.
Yeah.
You can see what people are going to use it for immediately. Here it's just not clear what the practical
all this commercial happening. I think the application probably is more than most other things we have seen.
Yeah, I mean, I think it's important, but it's hard to convince people.
And just to give you another example, this one, even for very established, at least in research, for example, video indexing and retrieval, I think 3 years ago when I was in IBM, Zhongsheng Li, he told me, said that I want to, set up some kind of benchmark system to evaluate it. Do you want to join me? I said, okay, well, of course. We have all suffered from the kind of database program, but nothing happened. But the track I picked that up. That's good. But he didn't do it. For track, it's easier because they got infrastructure there already. But if you want to start from scratch, it's pretty hard. But I certainly agree. First, what kind of database? I really think what kind of database you want here, because intentional or unintentional is quite different. That's the first problem. So even you study people who with the same background, speak the same language, it's not easy. If you want to collect the kind of language from different kind of culture and different language, that's almost impossible. It's very hard. Okay. But maybe let's get English correct first.
Maybe easier to get still photographs of people with genuine emotions than to get actual video. Still photographs are available on the web, and you can actually, it's still a process of sifting through hundreds of thousands of images to find these. But some colleagues of mine have been collecting databases of still images that way.
But the thing that you lost the kind of dynamic information there. Okay, that's
true.
Yeah.
The audio is not true.
The audio is actually, to me, seems more accurate.
Well,
It's actually how to have, be able to track, on a call. So someone call, customer service.
yes.
And I would like to get information that the guy's getting upset.
Yes.
So you actually have this sample, like the beginning. Suppose the guy is neutral at the beginning, and then that's how upset this guy is. It's like a supervisor.
Oh.
I think that would be actually more compelling.
But I thought there are the kind of commercial system available. Maybe something, some of these call center already used.
Yes, but I think mostly you have an operator here to handle that. I don't think it's a machine. Yeah, I don't think it's a machine because the machine can't handle this yet. Okay. As I said, I was surprised.
But it doesn't have to do all six. Right?
Yeah, of course. Yes.
Angry
Yes.
or not angry.
Yes. Yeah.
And this binary condition, they probably will be much higher. Right? If you get up 95%, that's not that high.
You're right.
Once you're angry, even if you make 10%
Since
error,
you
it
have
suits.
an operator, one easy solution is basically just press angry button. So you can basically press this
No,
button.
but it's
My
not.
problem is the opposite. Very often, for example, if I call an airline or something, and I'm getting upset, so at least 3 times,
And then if it's not
when the
automatic-
person realizes that I'm getting upset, the operator hangs up. Seriously, because they don't want their supervisor to see that they're not be able to handle my problem. And when they realize that I'm gonna want to talk with the supervisor, they just hang up.
Yeah, this is a very bad trend. It used to be, it's a transfer right now.
I have to be neutral up to the point of asking the name. I'm not trying
Right.
to. What's your name again?
Okay. Yeah.
Yeah, I think probably we should move to the next topic.
Okay, sure. Okay, let's go to the next topic. Honestly, for the next topic, I feel that I'm a student here because it's not exactly my field. I just lucky to have a student who have 5 years experience in with Cisco, and he worked in on the. Let's close this one. But he has done something which is quite interesting. I think in my abstract I said it's a peer-to-peer, but actually I think it's more it's better to call it a collaborative video streaming because it's not exactly. Some are peer-to-peer, others are not peer-to-peer. It's actually just use the complementary nature of some of the transmission media. Okay. What the model we use, actually this is not exactly complete because there's another model I forgot to include because he just did the simulation and math, etc. And I didn't put it here. So we talk about the integrated 3G wireless LAN networks, and we talk about the centralized peer-to-peer networks, which include one is the centralized, which is it's the internet. Okay, another one is actually the wireless LAN and the ad hoc, and essentially the what I call the MS. So that kind of combination of peer-to-peer, okay, which is completely wireless. Again, complete wireless, but within the WLAN. Normally, one component can provide reliable transmission in this architecture. For example, the server in the internet peer-to-peer network, or the 3G, and another provide high bandwidth and or convenience. For example, the one LAN in the integrated 3G and the peers in the centralized peer-to-peer networks. Now, this here is the first part, is wireless video streaming over integrated 3G and one LAN network. Okay, so the question, was that other presentation technical enough or not? Well, this one is okay. I essentially, because at his request, I put all the mathematics here. Okay, but I don't think we actually go through all the mathematics. Actually, mathematics is not that complicated. Okay, this project is supported by Canada Research Lab program and Canada Foundation for Innovation, and by my student Ivan Lee. He's a PhD student actually from University. He's a University student. He's one of the students I brought to Toronto, and he's going to graduate in a couple of months. So for the 3G and wireless networks, this is some of the characteristics here. For 3G, the throughput is normally low, and the coverage is large, and is more established. For the wireless LAN, throughput is normally high, but coverage is small, and which is not quite well established. So, the point is that can we use this kind of combination to do a scalable streaming transmission in wireless environment? So what we proposed is to use the readily established 3G system and high bandwidth and wireless LAN to make a good complementary part, so that we got a streaming server which goes to the IP network, and up to this point is either go to the 3G to the user, and other route is wireless LAN go to the user. So here, you can see that based on this one, you're going to need to this kind of handover between the wireless LAN, but also probably you have a handover between different 3G networks here. Okay, so essentially the principle here is that we want the base layer transmission to be reliable. So we use 3G system. And we'll transmit an enhancement layer where the wireless LAN, because enhancement layer, for example, in PFGS is actually has a much higher bandwidth requirement here, but it is not that fundamentally important as a base layer. Okay. Now we actually consider this the special characteristics of the wireless transmission, and come up with the extended Gilbert model to include the handovers in wireless communication. But essentially, you can see that from the previous slides, they go completely different lines. So the model used either for the 3G or for the wireless LAN separately. Both we set up this kind of model. Yes. Well, yes, it's essentially from one access point to another. Okay, yeah. So it has three states: good, bad, and handover. The handover state, we use a simple model. Okay, but of course the handover could from the good state directly, but we just simplified that. At this stage, to assume that handover only initiated from the bad state and come back from bad state, because when you get to the border. It's likely that it's possible, more likely that the state will get, the quality will get worse. And the steady state probability of being in the 3D states are defined as P1, P2, and P3 respectively. And from there, okay, the transition probability matrix is given by this equation. Okay, and from here, we will have the steady state is represented by this matrix, multiply the steady state vector should equal to the steady state vector. And then from the relationship between the transition probabilities, we have these three relationships given here. And if you substitute 3 into 1, you get that the P is given by this equation, which is just in terms of the, not of the, should 1, 2, 3, 4, 3, 7, but now we reduce to because we eliminated the kind of independent. We show the relationship, the dependency between the probability here. Okay, and from here, this the steady state probability should satisfy this equation, and then if we combine 1 and 3, these two rows of 2 and 5, you get this transition. So this vector matrix equation. From here, you can solve 6 to get a steady state probability, which is given by this expression, and A is given by this complicated equation here. And then from here, you get you substitute 3 and 8 back into this equation, and then the probability of steady state equation in terms of the transitional probability is given by this expression. And from this is a kind of the reason this is just to come up with a simulation parameter. We got this, and then we can do the simulation based on this. If you give the value of the transitional probability, and then you can do the to set up the simulation. There are a few things in error recovery. First, we consider the adaptive unequal error protection. Here, we just assume that it's probability there's possible some kind of gossip, some noise of the channel, and then we use the turbo code as a channel coding techniques. And here, we actually add an additional parity check mechanism to detect the corruption of the enhancement layer. The reason for that, if the enhancement layer is corrupted, it will affect the quality the video quality quite significantly, and then it would be great. It would be appropriate to discard the enhancement layer at that point. And the error recovery, another part is for the buffering for multipass latency. So in the integrated streaming system, of course, the latency will cause synchronization problem, and the multipass delay from two independent networks. Okay, if you failing to receive the enhancement layer within the real-time constraint, will result in a synchronization problem. There's two ways you can do. If enhancement layer doesn't come in a fixed time, you can drop it, or you can by providing it's memory, it's a memory buffer at receiver and some waiting, but of course that will delay the decoded bit stream, which again in turn will delay. What will affect any real-time transmission here. So it's always some pros and cons here. And then there is a problem for we need to try to handle the drifting error. We use the baseline profile in H.62 PFGS video coding. So the baseline profile only consider I and P right now. So right now we just use this model. And with the GOP, it's very interesting. Okay, with the GOP, the P frame reconstruction should be based on transmission of the previous frame. Here we actually define the length of GOP as .I here, and then if we assume the code is coded by CBR, and each frame at each layer have identical size. This is to simplify the scenario, which means that each code slice will have exact same amount of bits at the same layer. So that just makes it simple. Then we assume these three probability to be small, so that error pattern are bursty. This is kind of realistic assumption, because otherwise the network would be, you have terrible, transmission here. And then we can show that the average number of dropped frames is given by this equation for a period for a GOP. Now, but the point is that due to drift error, the loss occurred at bed or handover state will result in a sequence of video frame drop, because you lost one frame, especially for base layer, you can't reconstruct the next base layer, etc. So you have to wait until the next iframe to receive. So we investigated to use cubic spline to try to recover the lost frame. It's not recover to try to approximate the lost frames here. We studied two approaches. The first one is extrapolation based on buffered frame prior to the lost frame. And we also consider interpolation based on buffered frame prior to the lost frame and iframe immediately after the lost frame. So you can see this one again will cause some delay here, but this one will not cause delay. But the extrapolation normally don't give you as good result here. So here's the simulation. We carried out. We started three scenarios: wireless LAN, 3G, and 3G/wireless LAN. And we use MPEG-4 standard CIF sequence, QO, with resolution standard CIF resolution. And we use the 8.64 PFGS to encode the video with each frame of the coded bit stream is sliced into 400 bit per block. And extra stopping bits are used for frame loss less than 400 bits, so just to make the scenario simple. But of course, this is not the optimal way of transmission. We have one base layer and three enhancement layers are being transmitted. Of course, the base layer in this integrated network, of course, the base layer transmitted through the 3G and the enhancement layer via the wireless LAN. And in the channel error analysis, we just use white Gaussian with 3.5 dB EB/0.
Are you using your own? Are you writing your own 3D and wireless LAN stacks?
I don't think so. I think my student I don't think he read that, but how he got it, I don't know, to be honest. Okay, but
I was wondering how the simulation is basically on wireless. So for example, you have the AWGN is 5 dB. How do you translate that to packet loss?
Well, but this is just exactly he just did exactly the simulation, so you can create this kind of environment, I guess.
Are you using, for example, MFCC to simulate the environment?
Pardon me? Which one? Oh, you mean the simulation package, right?
NS2, I think, only simulate for Wi-Fi.
To be honest, I didn't go that detail, but I can ask my student on how he did this kind of simulation. Okay. As I told you, he just gave me the paper a few days ago before I came. Okay, honestly, this is not published, but doesn't matter. Okay. Okay. So of course we use this is just the architecture for the PFGS video codec, and I don't need to go into details because I'm sure you're all familiar with this. And for simulation, we set up this kind of these parameters. These are I probably should call the primary, transition probability, and other probability can be formed in terms of this probability here. And you can see that in general, the P01 is smaller for the 3G and larger for wireless. Oh, I think here's the error here. It shouldn't be 2.2. It should be smaller than this one, because you would expect that 3G will stay in a good state more often than the wireless. And that's the assumption here. Okay, and then, this is what the simulation result. For this one, we we just assume that we just the kind of videos we received, we don't count on that kind of effect. Here you lose a frame, and then all the rest of them can't be reconstructed. Which, especially if the base layer is lost, you don't reconstruct anything. We didn't take that into consideration in these three graphs. And then for here, we take that into consideration. So you can see here that for that simulation parameter, the one LAN, wireless LAN, have quite a number of drops here, and as well as the 3G, they all have some kind of completely drop here. And for the combination, for the combined transmission, there's only 1 point. Actually, there's nothing is being transmitted. Pardon me? That's a frame number. Frame number. Okay, it's about I think it's 300 frames here. Okay. The vertical is the mean. It's very interesting. Yeah, it's actually the combination of the different kind of enhancement layer value. But you can see that this is it's just the kind of, if it got that back, it just gave a fixed value here. It's not it's just counted that you got this frame. It doesn't reflect the real value at that point. And this is the kind of the to use this 3G the integrated network comparison between the WLAN and here, and which actually takes the decoder quality into consideration. So you can see that this one is the best among the three. And this is with the error added, just consider 3G. Of course, with error the performance will drop. This shouldn't be the mean. This is actually the PS, the probability the PSNR. For this one, it's 32 dB, and if you go back to this one here, where is it? Oh, I got this wrong. This one actually should show something like 35 dB, a little bit more than 35 dB. And then this is a cubic spline interpolation. In general, it's not that good. This is just to show this is but the interesting thing is that if you use too many frames before, I think here probably we use 2. It's very interesting. Here we use 4 frames, but the interpolation is actually very bad. Here you want to use 2 frames. The result is actually better, just extrapolation. Okay, and here is the use the 2 previous frame and the immediate iframe after the lost frames, and the result, well, it looks good, but is it really good? I think we can see some of the video qualities. For this one, I don't have a video. For next one, I have a video to show you, but for this one, I only got this fixed videos here. This is the cubic spline extrapolation. Is a cubic spline interpolation. So it's actually the extrapolation. I think it's actually better. You see here, this kind of artifacts here. It looks terrible. Although from the diagram, from graph, this one seems to be better, but in fact, the extrapolation seems to be better here. Okay, here's the summary. A collaborative streaming can apply for integrated 3G and wireless LAN to yield better video quality compared to standalone 3G or wireless LAN. So you use the unequal error protection with the turbo code, which can yield better error resilience. And the cubic spline interpolation, especially the extrapolation, probably can give you some extra qualities in this. I don't think this conclusion is exactly correct. From what I see the video frame, I think the extrapolation is actually better here. Okay, now this is the first part here with some mathematics, and then the second part is video streaming over centralized peer-to-peer network. For this part, I don't have mathematics, but have the kind of explanations why we do this and how we did that. This actually have two case studies. First part was also done by Ivan Lee, which is network. The internet version, and this one by Ethan He, which is on the wireless. It's essentially is a wireless LAN network. Okay, so first just some comparison between the client server versus the P2P. Client server is one node provide service and other nodes use the service. Single point of failure, high service guarantee, but simple access management. It has scalable program, and also it could have the bottleneck point of failure. Okay, which is here. Okay, and for P2P, ideally the complete P2P, each node uses and provides service. No potential central point of failure, but low service guarantee, which is quite understandable because everybody could switch off the computer or any electronic device. And the complex decentralized coordination, but it could be highly scalable. Okay, now we particularly focused on the centralized peer-to-peer streaming, and the design objective is that we want application layer. So it is an application layer, and so without the need of upgrading the underlying network infrastructure. And it doesn't have any additional services like DeepSeek that would require that kind of additional service on the network backbone, and it can handle the P2P, the kind of heterogeneity in uptime, computational capacity, and the bandwidth. Offer a few convenience here. So it's. It has offers centralized management for authentication, authorization, accounting, and guaranteed perceived quality of service, which is the base layer essentially, and the traffic offload to the non-guaranteed network, which is a peer-to-peer part of the infrastructure. And essentially, in general, it works like, for example, the peer A is looking for some kind of service. If you send a request to the central server, the server would look for, of course, it has a table there to show who actually already got this, for example, video on demand. Okay, which user within that particular area already got that particular movie, and then he will tell that peer, and if the peer is still on, of course, it will respond, and then at the same time, it will send the media, the base layer, from the server to the peer, and the peer A, and the peer B will send the enhancement layer to peer A. And so this is the kind of control which will between the peers and the central server. And this is a architectural comparison with the client server model. This is the point of failure, and this is a centralized peer-to-peer model. This is from server, root from server, and the root from the peer. Of course, the peer which is up. And so now that's a general architecture. And then here we show a couple of case studies. The first one is the centralized P2P streaming versus the deep server. The deep server is a IPQS architecture based on packet marking, and it can differentiate traffic classes according to requirements. So what should be higher priority, etc. We can discard low packets in low priority traffic class upon congestion. This is a kind of different from the conventional service because it doesn't need the end-to-end resource reservation. It's a kind of more. And here is a network topology we use, which is the peer-to-peer model we use. This is a streaming server. Goes through these routers here, and from here you have a few clusters. Normally you look. Well, I think essentially you look for within your own cluster, because going here, well, just here you have the kind of upload traffic, which normally the upload communication is pretty weak. Okay, if you go to the other neighboring cluster, it will be even worse probably. So so this is the architecture, and this is the simulation result we have. We test on the Formant sequence, and you can see that it has a the bottleneck bandwidth is about 3 Mbps, and you can see that it's have about 2 to 3 dB increase in the PSMR. And here it's the same thing for the news sequence, which is RQ sequence. Not just RQ, the male anchorman is also there. Okay, now I will show you. Okay, just to focus your attention to RQ's face. Use. Oh my God. Why? Well, cursor demonstration. It was working. Okay, I can do this. I can get in. Pardon me? I can just get into the directory to do this. Okay. Oops, tipsy. This is okay, just focus on RQ's face. You see that here for diffusive, there are quite severe distortion because some of the frame has to be dropped. Enhancement layer frame has to be dropped because of congestion. And then if you see the news, the peer-to-peer one, you see more details in RQ's face here, because well, okay. If you go back one slide. This is architecture. Okay, well, the bottleneck should be somewhere around here. Right? Between the
limits what's coming out of the server.
Yes. Okay. For example, if you have 10 guys, they ask for the same video. It's a waste of bandwidth, right? Okay. Okay. Its a simulation is actually performed based on. Okay, let's go back to this one. This is how the kind of the information flow. For example, peer A, let's just use the video on demand. We want a video. Let's see, Lord of the Rings. So
You have a diff serve.
Yes.
Biomal.
Yeah.
And you have a peer-to-peer Biomal.
Yeah. Yes.
You must have a simulation condition. Say this is the condition of the diff serve network. You got the cross traffic.
Well, the architecture, okay, the architecture, they are the same. They all use where is it? Okay, let's see. They all use the same one. For the diff serve, everything is going from here to that to whoever is requesting the video.
For example, for the peer-to-peer serve, one peer.
Yeah, okay. He will serve. He will when for example when this guy want a video, he will request that, and streaming server would search. Okay, he had some kind of table. Okay, somebody in this area already got this video, so let's just send the base layer to this guy, and ask it.
By the way, where is the peer which is sending video also to the
Oh no, it's here. It doesn't show here. Okay, it's just any of them who has that video. Okay, well, but this one will identify who is the video, or who is the guy who has the video, and of course he need to see that if this guy is online.
How did that one get the video?
Pardon me?
How did that one get the video?
How did which one get the video?
The one here that's
You mean? Oh, I'm running out of battery. Oh my gosh. it's a. I saw, this is a new battery I got. The old battery is about this big. It can last for 10 hours. And the new one is supposed to be the same because that was the first design. They said that we didn't have for the first time they said it was not very good, but it lasts for 10 hours. And but the connector was not very good. So I asked this guy, so you gave me the connector failed twice. The first time they sent me another connector. The second time they said, okay, we'll give you a new battery. There is another piece. Another piece, according to my research support, that piece was is just a charger. He said that you don't need that. You take this with you. I said, how long that would last? He said, should be the same as the old one, 10 hours. But doesn't seem to. Oh my God, that's so terrible. But actually, the next one is actually quite similar. It's just it's used, but of course, you're just talking about in the wireless LAN area, and then the AP will be the one who send you the base layer, and the ad hoc MS would send can send through one pass or two pass or three pass to the requesting peer the enhancement layer. So that's essentially what it. Of course, the quality is getting worse and worse. You're going to see, for that kind of thing, because even the wireless LAN itself is not very reliable. So you're going to see the quality is getting worse and worse. I do have the videos for that, but I don't have a battery for that.